Good morning to all. I am Karina from BSc Chemistry Honours second year. Today's my topic is from Pradeep's Physical Chemistry book by Dr. S.C. Khetarpal. Electrochemistry. Whenever a redox reaction is allowed to take place in a single beaker, it is found that the solution becomes hot. For example, when a zinc rod is placed in copper sulfate solution, the solution is found to be warmer as the reaction proceeds according to the equation. Zinc plus copper sulfate to form zinc sulfate plus copper. Similar results are observed when a rod of copper is placed in silver nitrate solution. The reaction taking place is as follows: copper plus silver nitrate to form copper nitrate plus silver. Thus, we conclude that whenever a redox reaction takes place in a single beaker, chemical energy in the form of heat is produced. By suitable means, it is possible to convert the chemical energy into electrical energy. A device used to convert the chemical energy produced in a reaction into electrical energy is called an electrochemical cell or simply a chemical cell. These are also called galvanic cells or voltaic cells after the naming of Luigi Galvani 1780 or Alessandro Volta 1800, who were the first to perform experiments on the conversion of chemical energy into electrical energy. How a redox reaction can be used to produce electrical energy leading to the formation of an electrochemical cell can be understood by taking the above two examples of redox reactions again. Redox reaction between zinc and copper sulfate, zinc plus copper sulfate to form zinc sulfate plus copper, zinc plus copper 2 positive ion to form zinc 2 positive plus copper. The reaction may be split into two half reactions as under: zinc to form zinc 2 positive plus 2 electrons, copper 2 positive plus 2 electron to form copper. The first reaction is called oxidation half reaction and the second is called reduction half reaction. The reaction obtained by adding the two half reactions is called overall reaction. Thus, if a redox reaction is allowed to take place in such a way that oxidation half reaction takes place in one beaker and reduction half reaction in other beaker, the electrons given out by the former will be taken up by the latter and a current will flow. This is achieved as follows. A zinc rod is placed in zinc sulfate solution taken in a beaker. A copper rod is placed in copper sulfate solution in another beaker. The two rods are connected by a wire and the two solutions are connected by a salt bridge. A salt bridge is a U-shaped tube containing concentrated solution of an electrolyte like KCl, KNO3, K2SO4, etc. or solidified solution of such an electrolyte in agar-agar and gelatin. The function of the salt bridge is to allow the movement of ions from one solution to the other without mixing of two solutions. Thus, whereas electrons flow in the outer circuit in the wire, the inner circuit is completed by the flow of ion from one solution to the other through the salt bridge. The complete setup may be shown in the figure. Some important feature of the above cell may be summed up as follows. The zinc rod at which oxidation takes place is called anode. The copper electrode at which reduction takes place is called cathode. Since electrons are produced at the zinc electrode, it is designated at negative pole. The other electrode acts as the positive pole, that is copper electrode. The electrons flow from negative pole to positive pole in external circuit. However, conventionally, this current is said to flow in the opposite direction. The oxidation of zinc into zinc ions produces excess of zinc 2 positive ion in the left beaker. Similarly, the reduction of copper ion to copper atom leaves the excess SO4 negative ion in the solution in the right beaker. To maintain electrical neutrality of the solution in the two beakers, the cations and the anions move through the salt bridge. This helps to complete the inner circuit as already mentioned. As copper from copper sulfate solution is deposited on copper electrode and sulfate ions migrate to the other side, the concentration of copper sulfate solution decreases as the cell operates. Consequently, the current falls with the passage of time. Evidently, the weight of copper rod will increase while that of zinc rod will decrease as the cell works. The cell based on above reaction is commonly called Daniell cell. A popular form of this cell is given in the figure. Here, salt bridge is replaced by porous port through which the SO4 negative ions migrate from copper sulfate solution to the zinc sulfate solution. Redox reaction between copper and silver nitrate solution. The reaction is Copper plus silver nitrate to form copper nitrate plus silver. Copper plus 2 Ag positive plus copper 2 positive plus 2 Az. The two half reaction will be copper to form copper 2 positive plus 2 electron, that is oxidation half reaction, and the reduction half reaction is 2 Az positive plus 2 electron to form Az. Hence the cell may be set up as shown in figure. Here oxidation takes place at copper electrode, therefore it acts as anode or negative pole. Reduction takes place at silver electrode, it acts as cathode or positive pole. The flow of conventional current is from silver to copper. Now the electrochemical cell based on the reaction is given as in the figure. What is an electrolytic cell? If the aqueous solution of an electrolyte or the molten electrolyte is taken in a vessel and two metal rods are immersed into it and then connected to a battery, the ions start migrating towards the electrodes, the cations towards the cathode connected to negative of the battery, and anions towards the anode connected to the positive of the battery. The anions on reaching the anode lose electrons, oxidation takes place. The cations on reaching the cathode gain electrons, reduction takes place. At anode B negative to form B plus electron, oxidation. At cathode A positive plus electron to form A, reduction. Thus a redox reaction takes place on supplying electrical energy resulting into the decomposition of the substance. Such an arrangement in which electrical energy is supplied to bring about the redox reaction, which is otherwise non-spontaneous, to bring about the decomposition of the electrolyte, a phenomena called electrolysis is called an electrolytic cell. Difference between electrochemical, galvanic cell or electrolytic cell. Electrochemical cell. It is a device to convert chemical energy into electrical energy. That is, electrical energy is produced as a result of the redox reaction taking place. It is based upon redox reaction which is spontaneous. The two electrodes may be set up in solution of same or different electrolytes. The former are called concentration cell. Electrode on which oxidation takes place is called anode or negative pole, and the electrode on which reduction takes place is called the cathode or positive pole. To set up this cell, a salt bridge or a porous pot is used. Electrolytic cell. It is a device to convert electrical energy into chemical energy. That is, electrical energy is supplied to the electrolytic solution to bring about the redox reaction. That is electrolysis. The redox reaction is non-spontaneous and takes place only when electrical energy is supplied. The two electrodes are set up in same electrolytic solution. The electrode which is connected to the negative terminal of the battery is called cathode, and the cations migrate to it which gain electrons, and hence reduction takes place here. The other electrode is called the anode. No salt bridge is used in this case. Representation of an electrochemical cell. An electrochemical cell is represented in a manner as described below. Zinc oblique zinc 2 positive, C1 concentration. Salt bridge Cu2 positive, C2 oblique Cu. By convention, the electrode on which oxidation takes place is written on the left hand side, and where a reduction takes place is written on right hand side. The electrode on the left hand side is written by writing the symbol of the metal or the gas, first followed by symbol of ion with its concentration in brackets. The electrode on right hand side is written by first writing the ion along with its concentration in brackets, followed by symbol of metal or the gas. Single vertical line represent the phase boundaries of electrodes and double line represent the salt bridge. C1 and C2 represent concentration of zinc 2 positive and copper 2 positive ion respectively. In a similar manner, copper silver cell may be represented as copper phase boundary copper 2 positive C1 concentration, salt bridge Az positive C2 concentration, phase boundary Ag. Electrode potential. In a cell, oxidation takes place at one electrode and reduction at the other. In other words, one electrode has the tendency to lose electrons while the other has the tendency to gain electrons. The tendency of an electrode to lose or gain electrons when it is in contact with its own ions in the solution is called its electrode potential. The electrode potential is further termed as oxidation potential if oxidation takes place at the electrode, and is called reduction potential if reduction takes place at the electrode. Further, if in the half cell the metal rod is suspended in a solution of unit activity and the temperature is kept at 25 degrees Celsius, the electrode potential is called standard electrode potential, represented usually by E naught. If a gas is involved, the standard conditions chosen are 1 atmospheric pressure and 25 degrees Celsius temperature to 98 Kelvin. EMF of cell and its measurement. The force which causes the flow of electron from one electrode to the other and thus result in the flow of current is called electromotive force, usually represented by EMF and measured in volts. Now the key is this force is described as. Now the key is removed from position A and inserted in position B so that the experimental cell X is in the circuit. The sliding contact J is moved along the wire AB till no deflection is observed in the galvanometer. Let us suppose that it occurs at point C. Then if Ex is the unknown EMF, we have Ex directly proportional length AC, Ex upon Es is equals to length AC upon length AC dash, Ex equals to length AC upon length AC dash into Es. Thus knowing Es, Ex can be calculated. Standard cell. A standard cell is a cell which fulfills the following requirements. It has a constant value of EMF which is reproducible. The EMF does not change with passage of time. The temperature coefficient of EMF is very low. The best known cell which meets the above requirements approximately is the Weston standard cell, the usual form of which is shown in figure. It consists of an H-shaped glass vessel. One of the limb contains mercury covered with a paste of mercurous sulfate and mercury. This limb acts as the anode. The other limb, which acts as the cathode, contains cadmium amalgam containing 12 to 14% of cadmium by weight, covered with crystals of solid cadmium sulfate and then saturated cadmium sulfate solution. Short platinum wires are sealed into the bottoms of the limbs to make contact with the active materials. The limbs are finally closed with corks and sealing wax. The purpose of placing solid crystal of cadmium sulfate is to keep the cadmium sulfate solution saturated at all temperatures. The EMF of the above cell is 1.0185 volt at 15 degrees Celsius and 1.0181 volt at 25 degrees Celsius. The reaction taking place in the cell is CD plus Hg2SO4 plus aqueous to form CdSO4.8 by 3 H2O plus 2 Hg. The cell is reversible in this sense. Reversible and irreversible cell. In thermodynamics, a reversible process is defined as a process in which the driving force is infinitesimally different from opposing force. The process can be reversed by applying force infinitesimally greater than the force already acting. The concept of reversible process is highly significant in thermodynamics because a number of relationships have been derived for the processes that are thermodynamically reversible. In a cell, chemical energy is converted into electrical energy. In order that the thermodynamic relation may be applicable to cell, the cell must operate under reversible condition. A cell is said to be reversible if it satisfies the following three conditions. If an opposing EMF equal to that of the cell is applied to the cell, no current should flow in the circuit and hence no chemical reaction should take place. If an opposing EMF slightly smaller than that of cell is applied, an infinitesimally small current should flow from the cell and an infinitesimally small reaction should take place. If an opposing EMF infinitesimally greater than that of cell is applied, an infinitesimally small current should flow in the opposite direction and an infinitesimally small reaction in the reverse direction should occur. If the above conditions are not satisfied, the cell is said to be irreversible. A well-known example of a reversible cell is that of Daniell cell, consisting of zinc electrode dipped in zinc sulfate solution and a copper electrode dipped in copper sulfate solution. When it is producing current, the reaction taking place in the cell is zinc plus copper 2 positive to form zinc 2 positive plus copper. When an opposing EMF equal to that of cell is applied, the reaction stops completely and no current flows at all. When an opposing EMF smaller than that of the cell is applied, a small current should flow from the cell and the above reaction is found to take place. If opposing EMF greater than that of cell is applied and current flow infinitesimal current flows in the opposite direction and the above reaction is found to take place in the reverse direction. In the potentiometric method for determination of EMF, as no current flows at the time of measurement, the conditions of reversibility is satisfied. Now let us consider the example of a cell which is irreversible. Consider a cell consisting of zinc rod and a silver rod dipped in dilute sulfuric acid. When two rods are connected with a wire, the following reaction takes place. Zinc plus sulfuric acid to form zinc sulfate plus H2. Zinc is oxidized to zinc 2 positive ion and H positive ion are reduced to H2 gas. In other words, zinc dissolves at one electrode, H2 gas is evolved at the other. Now, if the cell is connected to an external source of EMF, say a battery, whose EMF is slightly greater than that of cell and is opposing the cell, silver dissolves at one electrode and H2 gas is evolved at the other. 2Ag plus H2SO4 to form Ag2SO4 plus H2. Now oxidation takes place at silver electrode, reduction at the other. Thus, though the above cell can be made to satisfy the first condition of reversibility, that is, the direction of current can be reversed by making the opposing force infinitesimally greater than driving force. The second condition of reversibility is not satisfied. The chemical change is not reversed. Zinc plus 2H positive to form zinc 2 positive plus H2 does not become zinc 2 positive plus H2 to form zinc plus 2H positive. Instead, a new chemical reaction takes place. Hence, the above cell is not reversible but is irreversible. Such cells, however, do not have any thermodynamic significance. Reversible electrodes. Two electrodes of a reversible cell are called reversible electrodes. Each electrode is termed as reversible electrode because the half cell reaction occurring at the electrode can take place in the direct direction as well as in the reverse direction. The various reversible electrodes are classified into the following 5 different types. Metal ion electrodes. Number 1. Such an electrode consists of metal dipped in solution of its ions, zinc rod dipped in zinc sulfate, copper rod dipped in copper sulfate. Taking example of copper ion electrode, oxidation takes place at electrode. Reaction may be represented as copper to form copper 2 positive plus 2 electron. Reduction takes place at electrode, copper 2 positive plus 2 electron to form copper. Thus, the electrode is reversible with respect to copper ion. Number 2. Amalgam electrodes. These electrodes are just like metal ion electrode except that the metal is replaced by its amalgam, solution of metal in mercury. For example, zinc amalgam electrode consists of zinc amalgam dipping into a solution of zinc ion. The electrode is thus represented as zinc bracket Hg, face boundary zinc 2 positive. When oxidation takes place, reaction is zinc Hg bracket to form zinc 2 positive plus 2 electron. When reduction takes place, the reverse reaction is written zinc 2 positive plus 2 electron to form zinc Hg. Thus, the electrode is reversible with respect to zinc ion. Amalgam electrodes are preferred over metal ion electrode for following reasons. Equilibrium between amalgam and the ion is established more quickly than with the pure metal. Active metals like sodium, potassium, calcium, etc. cannot be used directly as electrodes in aqueous solution. However, by changing them into amalgam, their activity is reduced and then they can be used. The impurities present in metals, which sometimes cause erratic behavior in pure metals, are diluted by amalgamation to give satisfactory result. Number 3. Gas electrode. These electrodes consist of a gas bubbled around an inert metal wire or foil, usually of platinized platinum, immersed in the solution capable of furnishing the ion of the gas. The function of the metal wire or the foil is that firstly, it helps to establish the equilibrium between the gas and its ions, and secondly, it helps to make an electrical contact, that is, electrons lost or gained can flow through it. A few common gas electrodes are briefly described below. Hydrogen electrode. The design of the hydrogen electrode, which is in fact a general design for any gas electrode, is shown in figure. In the standard or normal hydrogen electrode, hydrogen gas at 1 atmospheric pressure is passed into 1 molar HCl acid in which the foil of platinized platinum remains immersed. When in a cell, this electrode acts as the anode. Oxidation takes place. Following reaction is H2 to form 2H positive plus 2 electron. Some hydrogen gas changes into H positive ion which go into the solution. When this electrode acts as cathode, reduction takes place. Following reaction occur 2H positive plus 2 electron to form H2. Some H positive ion from the solution change into H2 gas. Thus, the electrode is reversible with respect to H positive ion. This electrode is usually represented as Pt, H2 gaseous for face boundary H positive, concentration equals to C. Chlorine electrode. In this case, Cl2 gas at a given pressure is passed into HCl acid which is capable of furnishing the Cl negative ion. For oxidation to take place, 2 Cl negative to form Cl2 plus 2 electron, reduction to take place, Cl2 to plus 2 electron to form 2 Cl negative. Thus the electrode is reversible with respect of Cl negative ion. Third one is oxygen electrode. This electrode is reversible with respect to hydroxyl ion. Thus to construct this electrode, oxygen gas at a given pressure is passed into solution capable of giving OH negative ion. For reduction to occur, reaction taking place is O2 plus 2H2O plus 2 electron to form 4 OH negative. For oxidation to occur, the reverse reaction takes place. Number 4. Metal insoluble salt anion electrode. This is the most commonly employed category of electrodes. Here the electrode consists of a metal in contact with its sparingly soluble salt and a solution of a soluble salt containing the same anion as that of the sparingly soluble salt. A few examples of electrode of this type are silver chloride, potassium chloride electrode, prepared by dipping a silver wire in KCl solution to which a drop of AgNO3 is added to form AgCl. Number 2. PbSO4 K2SO4 electrode, prepared by dipping a lead wire in K2SO4 solution to which a few drops of lead nitrate solution are added to form PbSO4. Number 3. Hg2Cl2 KCl electrode, calomel electrode. This is most frequently used electrode as shown in figure. It is prepared as follows. Pure mercury is placed at the bottom of a tube T. It is covered with a paste of mercurous chloride calomel and then filled with either dasychromal or normal or saturated solution of KCl from the side tube A such that the side tube B ending into a jet is also filled with the KCl solution. A tube C having a piece of platinum wire sealed at its end is fixed into the tube T such that the platinum wire remains dipped into the mercury. A little mercury is placed in tube C and a copper wire put into it to make an electrical contact. An alternative form of calomel electrode used very frequently in the laboratory is shown in the figure. Oxidation can occur at this electrode through the following reaction. 2Hg to form Hg2 positive plus 2 electron, Hg2 positive plus 2 Cl negative to form Hg2Cl2. Overall reaction is 2Hg plus 2 Cl negative to form Hg2Cl2 plus 2 electron. And when reduction takes place, the above reaction occurs in the reverse direction. And overall reaction is Hg2Cl2 plus 2 electron to form 2Hg liquid plus 2 Cl negative. This overall reaction is just the reverse of the overall reaction when oxidation takes place. Hence, the calomel is reversible with respect of chloride ion. Number 5. Oxidation reduction electrode. These electrodes are prepared by dipping a platinum wire into the solution of two salts of same metal but having different valencies. For example, ferrous and ferric salt, stannous and stannic salt, or serous or ceric salt, etc. The EMF arises because of the tendency of the metal ion in one oxidation state to pass into the second more stable state. The function of platinum wire is merely to pick up the electrons and to make an electrical contact to the electrode. The reactions taking place in such an electrode may be represented as follows. Fe2 positive equilibrium Fe3 positive plus electron, Sn2 positive equilibrium Sn4 positive plus 2 electron, Ce2 positive equilibrium Ce3 positive plus electron. Relationship between electrical energy and chemical energy. The electrical energy produced in a cell is defined as the product of quantity of electricity that passes through the cell and the EMF of the cell. Electrical energy equals to quantity of electricity into EMF. For every 1 mole of electron transferred in the cell reaction, the quantity of electricity that flows through the cell is 1 Faraday, which is equal to 96500 Coulomb. Thus, if n moles of electron are transferred in any cell reaction, the quantity of electricity passing through the cell equals to Nf Faraday. If E is the EMF of cell, then electrical energy equals to Nfe. Till the middle of 19th century, it was generally accepted that the electrical energy produced in a reversible cell was equal to the chemical energy, measured as heat when the reaction takes place in a single beaker. This view was supported by following result. In Daniel's cell, N equals to 2, hence in order that 2 gram equivalent of copper may be deposited or 2 gram equivalent of zinc may dissolve, 2 Faraday of electricity must flow through the cell. Further, for this cell, E equals to 1.10 volt. Hence, electrical energy produced equals to 2 into 96500 into 1.1 joule equals to 212300 joules. The heat produced when 2 gram equivalent of zinc react with the same copper sulfate solution in a single beaker is found to be nearly 2,12,000 joules. This is in good agreement with the electrical energy. However, later on it was observed that for a large number of reactions, the electrical energy produced was not equal to chemical energy. Hence, it was suggested by Gibbs 1875 and Helmholtz 1882 that the electrical energy produced in a reversible cell is equal to the decrease in free energy accompanying the cell reaction. Thus, if del G represents change in free energy, we must have minus change in G equals to NFE according to Gibbs-Helmholtz equation. Delta Z equals to delta H plus T curly by curly T of delta G at constant pressure. Substitute the value of delta G minus NF equals to delta H plus T curl upon curl T minus NFE at constant pressure. NFE equals to minus curl delta H plus T NF curly E upon curly T at constant pressure. E equals to minus delta H upon NF plus T curly E upon curly T at constant pressure. From equation, it is evident that whether electrical energy NFE produced is equal to, less than or greater than enthalpy change depends upon the sign of del E upon del curl E upon curl T, that is the temperature coefficient of the EMF. Thus, if d upon dt is extremely small, almost equal to 0, as in the case in Daniell cell, the electrical energy produced is equal to enthalpy change. If curly E upon curly T is positive, the electrical energy produced is greater than the heat of reaction at constant pressure, the additional energy being absorbed from the surrounding. If curly E upon curly T is negative, the electrical energy produced is less than the heat of reaction at constant pressure, the difference of energy being lost as heat to the surrounding. Calculation of thermodynamic quantity of cell reaction. Delta Z equals to minus NFE. Delta H equals to NFT curly E upon curly T at constant pressure minus E. Knowing the EMF E and the temperature coefficient of the EMF curly E upon curly T at P, the heat of reaction delta H can be calculated. Having known the values of delta G and delta H, the entropy change delta S accompanying the reaction can be calculated using the relationship delta G equals to delta H minus T delta S. Delta G minus delta H equals to T curly upon curly T of delta G at P equals to T curly upon curly T of minus NFE at constant pressure equals to minus NF T curly E upon curly T at P. Delta G minus delta H equals to minus T delta S. Now comparing these equations, minus T delta S equals to minus NF T curly E upon curly T at constant pressure, and delta S equals to NF curly E upon curly T at constant pressure. Now the next topic is standard hydrogen electrode and measurement of electrode potential. The term electrode potential and standard electrode potential have already been defined in the above sections. The absolute value of potential of a single electrode cannot be determined. It can only be measured by using some electrode as the reference electrode. The reference electrode used is the standard hydrogen electrode, in which H2 gas at 1 atmospheric pressure is bubbled around a platinum foil dipped into acid solution having 1 molar, having H positive is equals to 1 molar. The electrode potential of standard hydrogen electrode is taken as 0. To determine the electrode potential of any electrode, a cell is set up using this electrode as one of the electrode, and second electrode is standard hydrogen electrode. The EMF of the cell is measured, as the EMF of cell is sum of oxidation potential of electrode where oxidation takes place and reduction potential of the electrode where reduction takes place, and one of the electrode involved is the standard hydrogen electrode, for which the electrode potential is taken as 0. The EMF of the cell will directly give the electrode potential of the electrode under investigation. The direction of the flow of current further indicates whether oxidation takes place or the reduction takes place on the electrode under investigation with respect to the hydrogen electrode. Accordingly, the electrode potential is termed as oxidation potential or reduction potential. The determination of electrode potential may be further illustrated with the help of the following two simple examples. Determination of standard electrode potential of zinc 2 positive electrode. A cell comprising of zinc electrode immersed in 1 molar zinc sulphate solution and a standard hydrogen electrode is set up as follows. EMF of above cell comes out to be 0.76 volt. Hence, standard electrode potential of zinc 2 positive electrode equals to 0.76 volt. Further, the direction of flow of current indicate that oxidation take place at zinc electrode. Hence, 0.76 volt is the standard oxidation potential of zinc 2 positive electrode. Determination of standard electrode potential of copper 2 positive electrode. A cell comprising of copper electrode immersed in 1 molar copper sulphate solution and a standard hydrogen electrode is set up as follows. EMF of cell comes out to be 0.34 volt. Hence, standard electrode potential of copper 2 positive electrode equals to 0.34 volt. Further, the direction of flow of current indicate that reduction take place at the copper electrode. Hence, 0.34 volt is the standard reduction potential of copper 2 positive electrode. It is important to mention here that it is a most common practice to express all the electrode potential as reduction potential. Since the reduction half reaction is just the reverse of the oxidation half reaction, therefore reduction potential is obtained from oxidation potential by simple changing the sign for any electrode. Reduction potential equals to minus of oxidation potential. Other reference electrode and measurement of electrode potential. The use of hydrogen electrode as the reference electrode is not convenient obviously, because it involves the use of H2 gas. Hence, a number of other electrodes have been used as reference electrode. The most common out of these is the calomel electrode, the construction of which has already been described in figure. The electrode potential of calomel electrode at 25 degrees Celsius using 0.1 normal KCl, 1.0 normal KCl and saturated KCl solution have been determined accurately. These are given below as reduction potential. 0.1 normal KCl solution, its reduction potential is 0.3338 volt. 1.0 normal KCl 0.2800 volt. Saturated KCl solution plus 0.2415 volt. To determine electrode potential of an electrode, a cell using this as one of the electrode and calomel electrode as the second electrode is set up. The EMF of cell is measured and then the following expression is used to calculate the required electrode potential. EMF of cell equals to oxidation potential of electrode where oxidation take place plus reduction potential of electrode where reduction take place. The calomel electrode using 0.1 normal KCl solution is usually preferred because it has lowest temperature coefficient. However, the calomel electrode using saturated KCl solution is convenient for many purposes and is often used. The method of determination of electrode potential using calomel electrode as the reference electrode and may be illustrated with the help of following example. Determination of standard electrode potential of zinc 2 positive electrode. A cell comprising of zinc electrode immersed in 1 molar zinc sulphate solution at calomel electrode say using 1 normal KCl solution is set up as follows. EMF of cell above cell at 25 degrees Celsius comes out to be 1.083 volt. Further, direction of flow of current shows that oxidation takes place at zinc electrode. Hence, we have EMF of cell equals to oxidation potential of zinc electrode plus reduction potential of calomel electrode. 1.083 equals to oxidation potential of zinc electrode plus 0.280. Therefore, oxidation potential of zinc electrode equals to 1.083 minus 0.280 equals to 0.803 volt. Number 2. Determination of standard electrode potential of copper 2 positive electrode. This cell comprising of copper electrode immersed in 1 molar copper sulphate solution and calomel electrode. EMF of above cell comes out to be 0.018. Further, the direction of flow or current shows that reduction takes place at the copper electrode. Hence, we have EMF of cell equals to oxidation potential of calomel electrode plus reduction potential of copper electrode. 0.018 equals to minus 0.280 plus reduction potential of copper electrode. Reduction potential of copper electrode equals to 0.018 plus 0.280. which is equals to 0.298 volt. Similarly, silver chloride electrode has also been used as reference electrode. Its electrode potential, standard electrode potential expressed as reduction potential, has been found to be 0.02224 volt at 25 degrees Celsius. Electrochemical series. The standard electrode potential of a large number of electrodes have been determined using standard hydrogen electrode as the reference electrode, for which the electrode potential has been arbitrarily fixed as 0. Also, as already mentioned, it is a practice to express the electrode potential as reduction potential, since reduction half reaction is just reverse of oxidation half reaction. The reduction potential of electrode is obtained from its oxidation potential by simply changing the sign. Further, according to the latest convention of sign, the electrode at which reduction takes place with respect to standard hydrogen electrode has a positive oxidation potential, or expressed as reduction potential, it will have a negative sign. The various electrodes have thus been arranged in order of their decreasing values of standard reduction potentials as shown in table 6.2. This arrangement is called electrochemical series. Applications of the electrochemical series. Number 1. To predict the relative ease of oxidation or reduction of various elements. As by convention, positive sign is used to represent the reduction potential. This implies that greater is the reduction potential, more easily is the substance, element or ion reduced, or in other words, strong oxidizing agent it is. As F2 has the highest reduction potential and Li positive ion has lowest reduction potential, this means that F2 is reduced most easily, whereas Li positive ion are reduced with greatest difficulty. In other words, F2 is strongest oxidizing agent, where Li positive ions are weakest oxidizing agent. Conversely, written the reaction in the reverse order, it can be postulated that lithium Li will be oxidized more easily and hence is best reducing agent, whereas fluoride ion F negative are oxidized with greatest difficulty and hence are weakest reducing agent. Now, the standard reduction potential at 25 degrees Celsius of is given as below. Number 2. To predict whether a metal reacts with acid to give hydrogen gas. In order that a metal M may react with an acid to give H2 gas, the following reaction should take place. M plus H positive to form M positive half of H2, which can be split into two half reaction. Oxidation half reaction is M to form M positive plus electron. Reduction half reaction is H positive plus electron to form half of H2. That is, the metal should have the tendency to lose the electron, undergo oxidation with respect to hydrogen. In other words, the metal would have a negative reduction potential. Thus, all metals lying below hydrogen in the electrochemical cell series react with the acid to give hydrogen gas. Further, evidently, lower the reduction potential, higher is the reactivity. Alternatively, as will be seen later, the EMF of cell comprising of the oxidation half reaction and reduction half reaction as written above may be calculated by adding the oxidation half potential and the reduction half potential. If EMF comes out to be positive, the reaction takes place. Number 3. To calculate the standard EMF of any electrochemical cell. As electrochemical cell is based on a redox reaction which can be split into two half reaction, that is oxidation half reaction, reduction half reaction. Standard EMF of cell equals to standard oxidation potential of oxidation half reaction plus standard reduction potential of reduction half reaction. Also, as oxidation potential equals to minus of reduction potential, the above expression may also be written in the form. The effective concentration of an ion or the electrolyte in a solution is called its activity. The activity of an electrolyte in a solution is usually represented by A. It is related to the actual concentration expressed as molality M by the equation A equals to gamma into M, gamma equals to A upon M, and where gamma is the activity coefficient. Activity coefficient may be defined as the ratio of activity to the actual concentration molality of the solution. For real solution, activity is not equal to molality. Hence, gamma is different from unity. For ideal solution, that is for very dilute solution, A equals to M and hence gamma equals to 1. It is observed that as the concentration is increased, the activity coefficient first decreases below unity, passes through a minimum and then begins to increase and then may attain values much greater than 1. It may be mentioned that activity of electrolyte is in fact the product of activity of its ions for univalent electrolyte. A equals to A positive, A negative. A positive negative is equals to under root of A equals to under root of A positive into under root A negative. In a similar manner, the term mean activity coefficient gamma plus minus has been introduced. For a univalent electrolyte, it is defined by the expression gamma plus minus equals to under root gamma plus gamma minus. A plus equals to gamma plus m plus and A negative equals to gamma negative m negative. A plus minus equals to under root of A equals to under root of gamma plus m plus into gamma minus m minus. For a univalent electrolyte, m positive equals to m negative equals to m, gamma positive equals to gamma negative equals to gamma plus minus. Under root A equals to under root of m square gamma plus minus square, A equals to m square gamma square plus minus. The determination of activities and activity coefficients has been discussed later in standard state. The standard state of substance is defined as that state for which the activity is unit. For ideal behavior, the standard state of a gaseous substance implies that its pressure should be 1 atmosphere, and for ideal solution, the standard state means that its molality should be unity. Further, the activity of a pure liquid or a pure solid is always 1, hence they are always in the standard state. Thank you.